Okay, so we're going to follow on from last week's BizChem 2 stuff by moving on to an important property of larger molecules, and it has consequences in a number of situations, but that property derives from the large size, and it's a concept which we call non-ideality. Solutions of molecules, particularly large molecules, don't always conform to the regular rules, and this makes them interesting to deal with, I suppose. And from an environmental sciences point of view, this covers the large polymer molecules, which are parts of plastics and things we hear so much on the news about. So that is important in terms of affecting the properties and in terms of trying to understand them and deal with them or utilize them. And just to introduce that, I'm just going to share my screen, and I hope this comes out okay. Right, so can you all see that?
Yeah.
It's like going to the opticians and looking down one of those things, and you know, where they do the eye tests and checking the intensity, looking at dots and all this sort of stuff. So this is not an optician's test, folks, you'll be pleased to hear. So you should be able to see a sphere, and the center of the sphere is marked by a red dot. Now imagine this sphere is a molecule, a macromolecule, a globular type of macromolecule. So it could represent a protein, although no protein is a perfect sphere, but some, like hemoglobin, could approximate to spherical shapes. So imagine this as a molecule, maybe hemoglobin or some other large polymer, which is sitting happily in solution, which is colored black, just for just so we can see the molecule more clearly. Now, watch what happens next. The molecule, by the way, isn't really stationary in a solution. It's moving around through Brownian motion. But for the sake of this illustration, let's keep that molecule fixed and watch what happens next. Okay, you should see another molecule come into the screen now, white, and it's moving in solution. And oh gosh, it's stopped from moving into this region of the solution that this molecule occupies. So it's not allowed to freely move in all parts of the solution. This time we've got a ellipsoidal molecule, and another ellipsoidal molecule is coming in, and the center of that molecule is blocked from a volume of the solution caused by the presence of this one. And the volume, which is what we call excluded from the center of this molecule, depends on the orientation. So this time it's coming in lengthwise on, and the center of that molecule is excluded from this volume of solution caused by the presence of that. So the shape and the orientation of the molecules are important in this effect, and this is called the exclusion volume effect. It's where molecules in solution, or macromolecules, are blocked from freely moving into part of the solution caused by the presence of other molecules. And if I go back to this one again, it's not just this volume which is excluded by the from another molecule coming in, from the center of another molecule coming in. Let's have this white sphere coming in again. Here it comes. Note the center of that sphere. You can see it traces around this large circle. So it's not just this volume which is excluded to the center of this molecule because of the presence of this one. It's actually a much larger volume caused by also the physical size of this. So this exclusion volume will depend on the size and also on the conformation, ellipsoid, or whether it's elongated, of the different molecules. This is an example of what we call non-ideal behavior. Okay, all get that?
Yeah.
Okay, fine. Right, then remember that then. Just remember that example. We'll just stop sharing that screen. And now I'll share another screen. So go to Windows again. And there should be a PowerPoint presentation waiting there. Okay, why is there no? Apologies for this, folks. I can't seem to find the presentation. Right, it's not there. Okay, let's just find this file. I might have to share the whole screen in order to show this, in which case I won't be able to use the mouse key. Let's try again. Okay, yeah, I might have to use the regular presentation. Let's go down again. Can't understand why that's not showing. Okay, I've got that on there. Let's try once more. Okay, if this fails, you have to go to the full screen. Refresh that. Window. Right, we got it. Okay, folks, can you all see that?
Yeah, I can see that.
Yeah.
Just move that back to start of the presentation. Okay, so we're going to now look at this non-ideality phenomena of macromolecules, and then we'll cover molecular weights of molecules, which is not quite as straightforward as you might think it is. But before we deal with non-ideality, we're going to deal with one particular solution property of molecules, and that's osmotic pressure, because that allows us to illustrate the non-ideality problem very well. But before I do so, let's just consider this equation here. Okay, it's on full screen now. So can you all see that equation? PV equals N
Yes.
R T.
Yeah.
Have you all met that equation before?
Yes.
Yeah.
Okay. It represents the properties of gases. P is the pressure. V is the volume occupied by the gas in a container. R is the gas constant, universal gas constant, and T is the temperature, an absolute temperature in degrees Kelvin. And N is the number of moles, where 1 mole is the Avogadro's number, 6.02 times 10 to the power 23 molecules. So, in your opinion, and you can turn your microphones on, in your opinion, what's the most interesting thing about that equation? In your opinion, if there is anything interesting, you may think there's nothing interesting, but in your opinion, is there anything interesting in that equation? And if so, what's the most interesting thing about that equation? Hang Zhao, what do you think about that equation?
Looks good.
Yeah, it is good. Is that the most interesting thing?
Yeah.
Okay, Zhang?
Well, it looks nice and neat, and
I don't mean in terms of the format on PowerPoint. I mean the
Yeah,
actual equation itself. Yeah.
I don't know, like PV over T is a constant. I don't know. I
Okay.
don't know.
Okay. Lafika, have you got any comments about this equation? Why it's interesting?
Like PV on, like as Z said, like PV on T is constant. That's the most interesting part for one molecule.
Okay, I suppose that's interesting. But from my point of view, I think the most interesting thing about this equation is that it's wrong. Okay, it's wrong in the sense it doesn't apply to real molecules. It's the ideal gas equation, and the ideal gas equation, PV equals nRT, assumes that there are no interactions between the gas particles, no repulsive, attractive interactions between the gas particles. One, and the other one assumption that's made is that the actual volume of the gas particles themselves is infinitesimally small. So the actual particulate volumes are small, although the volume the whole gas occupies is finite. So real gases are not like that. I mean, this is an approximation, and the approximation gets better as the numbers of molecules reduces. So by reducing the numbers of molecules, you reduce the interactions and you reduce the finite volume of the gas particles, or total finite volume of the gas particles themselves. And there are various corrections to this to cope with departure from this ideal behavior. So corrections to describe what we call non-ideal behavior, such as the Van der Waals approximation. And there are various what we call virial expansion coefficients that can be applied to this equation. So the equation is wrong. It's only an approximation in that sense, and the approximation gets better as the concentration of the gas gets less, or the concentration numbers of gas particles gets less, and the equation becomes worse as the concentration or the numbers of gas particles increases. So that, in my opinion, is the most interesting thing about the equation. It's not quite right. It's not. It's only an approximation. Right. Have you all met this equation before?
No.
No. Latika?
Yeah, I've learned, like, I've studied about it.
Okay, that's good. So this is Greek letter pi, capital Pi, and that represents what? Pi is the, it's not the pressure, it's the osmotic pressure of a solution of molecules. Okay, so it moved from gases now, this equation, to, this is the ideal gas equation, this equation, which represents solutions of molecules, solutions of molecules, solutions of macromolecules. So pi is the osmotic pressure of the solution. R is the gas constant again. T is the absolute temperature in degrees Kelvin. And C, little c, is the molar concentration. That's the number of moles per unit volume. So effectively we move B over to this side of the equation. And this represents the osmotic pressure of a solution of molecules. Zezang and Hangzhou, have you met osmosis before?
No.
Yes.
Do you know what osmosis is?
I know what it means, but
Okay.
like,
well, pi is the Greek letter pi is the pressure due to osmosis, or the osmotic pressure. So this is the corresponding equation to this one for gases for solutions of molecules. Right, guys. What's the most, and Latika, sorry, what's the most interesting thing in your opinion about this equation then? Latika, you know about osmotic osmosis. What's the most interesting thing in your opinion about this equation? Bearing in mind the discussion we just had on this equation.
Yeah, again, like, it only applies for the ideal case, maybe.
Absolutely. The most interesting thing about this equation is it's wrong. It only applies to ideal solutions which don't exist. It doesn't apply to real solutions of molecules. And the assumptions are a little bit different from this one, where we assume that the particles had no volume themselves and there were no interactions. With the ideal solution equation, we assume that the interactions are uniform. So the interactions between the macromolecules and the water molecules or the solvent molecules which they're dissolved in is the same as the interactions between the solvent molecules, and is the same as the interactions between the macromolecules. So we're assuming uniformity of interactions in the solution. And in terms of the volume, we are assuming that the volume of the macromolecule, or molecules that are dissolved, we assume that these volumes are identical to the volumes of the solvent molecules. So we're assuming that our macromolecule has the same volume as a water molecule. And that assumption gets worse the larger the particles are. And of course, the assumption of that, and also the assumption that we have uniformity of interactions, if there are any departures, if the macromolecules are interacting with each other, for example, then that situation will get worse as the concentration, the molar concentration increases. So the greater the concentration, the more the departure from ideality, or the greater the non-ideality. The lower the concentration, as we lower the concentration, get more dilute and more dilute, the more we approach the ideal solution conditions. Okay, so that's the ideal solution equation, which doesn't apply to real situations, but becomes steadily a better approximation as the solution becomes more and more dilute. Right, this brings us on to the topic of osmotic pressure of solutions and molecules. This, if you like, is the simplest solution property in order to illustrate this non-ideality phenomena. So, Lathika, I guess you're the only person that's met osmotic pressure before, is that right?
Yes, I have.
Hang Zhao, Zhang, you've met osmosis but not osmotic pressure, is that right? Yeah.
Mm-hmm.
Okay, so let's just illustrate this. Now let's imagine a container, okay, and it's got two outlets to the outside, to the atmosphere, and the container is got two compartments, and the compartments are separated by what we call a semi-permeable membrane. And in this side is just solvent, which we represent as A, so it could be water. And on this side, it's solute, which is B plus A, solvent. So this is the solution. So you've got solution this side and pure solvent this side. And by solvent, we mean any molecules that can freely pass across the semi-permeable membrane. So depending on what the material is, the solvent could be water, it could be a buffered salt solution, so long as the salt ions can move across and the buffer ions can move across. This will be the solvent A, and this is A plus B. Now, you've got solvent in contact with solution here. So you've got no macromolecules this side and macromolecules this side. Now, this is thermodynamically unfavorable because from a free energy point of view, nature requires a minimum of free energy, and that means in this case maximum entropy. So everything is randomized. So it wants everything to be spread out. So you have equal concentrations of A and B on both sides of this membrane. But it's not easy to accomplish because only the solvent can move through. The solute can't move through. So to try and make everything the same concentration, solvent will move through the semi-permeable membrane to make this as dilute as possible, as close to this as possible. So more and more solvent will move through. And as it moves through, the volume inside this container will move through, and this height here, or this outlet, will increase and increase and increase. And as it increases, a hydrostatic pressure builds up. So the higher this difference between these levels here, the higher the pressure difference. You call this the osmotic pressure, the pressure due to this process here, which is called osmosis. And there'll come a point where the solvent has gone through, until this pressure head here stops any more solvent going through. And the difference in levels between here and here, when it stops, is the osmotic pressure. And of course, you need to correct. You measure that as a height of water column, and you need to correct that to standard pressure units, newtons per meter squared, or so forth. So by moving through this direction, we're trying to minimize the free energy of the system until the pressure buildup is sufficient to arrest any more. And yeah, there's a simple formula linking the height of the column with the osmotic pressure, and it's simply, you can see my screen where you are. Maybe if we have to stop sharing, just go there. Okay, we'll reshare that in a minute, but it's simply let's try this. Okay, so pi equals h, which is the height of the column, times rho, which is the density of the liquid, and g is the acceleration due to gravity, which is in SI units 9.81 meters per second squared. So that's how we calculate the osmotic pressure from the height of the column. So that's all osmotic was. You can go into more complicated theory, which involves. I think I've showed that's wrong. Sorry, folks, I didn't mean to share that. Let's just. Right. I didn't mean to share that, folks. That was a mistake. Okay, what can you see now, folks?
PowerPoint slides.
Yeah.
Can you see just one screen, which is the slide again, folks?
Yeah.
Yes.
All right. There's nothing else on the screen too.
No.
Am I on the screen or not?
It's on presentation mode.
Okay, so all you can see is the screen.
Yeah.
Fine. Right, so if we go back to the ideal equation again, pi equals C R, which is the gas constant, times T, which is the absolute temp. Just excuse me 1 minute. I think there's some disturbance coming from. I'll just close the door there. Right, so we just rearrange the molar concentration C, and we know from last time that the molar concentration is the weight concentration in grams per mil or kilogram per meter cubed or whatever, divided by the molar mass in the appropriate units. Now, in this case, it's more convenient if we stick with SI units as opposed to CGS units, so we can keep with the SI units of pressure, which is the Newton meter squared or Pascal. So pi equals molar concentration times RT, or in terms of weight concentration, pi equals weight concentration divided by the molar mass, molecular weight, in the appropriate units, times the gas constant in the appropriate units, times the absolute temperature. So in SI, pi is in newtons meters squared, the gas constant 8.314 joules per K per mole, and the concentration is in kilogram meter cubed, and the molar mass is in kilograms per mole. In CGS, the corresponding unit in CGS units is dyne per centimeter squared, and the gas constant is the same numerically. You've got this 10 to the power 7 here, and the concentration is in grams per mil and molar mass in grams per mole. So you can either work in these units and convert to this this later, or vice versa, whichever is convenient. Right, so that's ideal behavior. So that's doesn't apply to real systems, real solutions of molecules, but solutions at low dilution, as you get more and more dilute, approximate this equation. But we can't always work under dilute solution conditions. We want to know what happens under real solution conditions, which can go to high concentrations. So we need to correct this term, either in this form or in this form, to allow for non-ideality. And to do that, we need to take into account these non-equal interactions between the molecules in a solution, and the fact that the particles have a much larger volume compared to the solvent molecules. If you remember that animation I showed you at the start. So what we do is just rearrange this equation slightly so that the concentration comes down to this side of the equation, okay? That becomes pi divided by C equals RT over M. So we just rearrange that equation, the ideal equation, because that puts it in a form which we can easily modify to allow for non-ideality conditions. So just to reiterate, the ideal equation assumes that the molecules, macromolecules, have the same volume as the solvent water molecules in which they're dissolved. This is not the case and leads to co-exclusion phenomena. Excluding means the molecules are excluded from the free movement into the parts of a solution caused by the presence of these other molecules. So molecules basically getting in the way of each other. And also interactions between the macromolecules are assumed to be the same as between the solvent molecules and the solvent macromolecule interactions. This will not be the case for macromolecules carrying a net positive or negative charge. And we call this charge behavior polyelectrolyte behavior. I think I mentioned polyelectrolyte, polyanions, polycations last time. Right. Can you now? I've just changed the screen. Can you see me on the screen now, or are you still in full presentation mode?
We can see you.
Okay, right.
We can see the presentation as well.
Yeah.
Okay, so let's imagine the fire alarm goes off now, and the door over there, the escapes over there. Now, if I'm the only person in the room, if I try to escape, it's very easy. I just go straight to the door, no one's in the way, out the door and out the building. But if this room was full of students, even with social distancing, but if it was full of students, then if the fire alarm went out, then it would take me a longer time to get out because we would be getting in the way of each other. Okay, and then if the students had just been to the farm at the back of the campus in the pig sheds and been cleaning out the pig sheds and come in here, there would have been a bit of a pong. So in trying to get out of the room when the fire alarm went off, not only would there be a problem because people would be in the way, but also because it just come from cleaning out the pig sheds, there would be sort of repulsive interactions, which would also hinder the movement. So these effects are concentration dependent. The higher the concentration, then the greater these effects. So any correction formula we apply here has to take into account the concentration, the sizes of the molecule, and the charges. And the simplest way of doing this is to add a correction term. And this is the correction term here, B. It's called the second thermodynamic virial coefficient, B. And what value would be BB, for an ideal solution? Zero, that's right. If it's zero, this term goes to zero. C is the concentration again. And this term is recovered. So as the concentration C becomes lower and lower and lower, this term becomes lower and lower and lower. And this correction equation approximates the ideal equation. And we can just expand this equation if you like. So pi over C equals RT over M plus B RT times the concentration. Right, so that's strange. So this is a correction coefficient, which we call the second thermodynamic virial coefficient. If that's the second virial coefficient, virial means expansion series, what's the first virial coefficient?
One.
1 over M. Okay, it's 1 over M. That's the first virial coefficient. This is the second. And then we've got other terms in C squared, C cubed, and C4, which are added. These would be added if we were dealing with very concentrated solutions. But we're just dealing with dilute solutions here, where a single correction term is sufficient. So this is called a second virial coefficient. It's a very close Lathica. You're up on the right lines. The first virial coefficient is here. It's actually 1 over M is the first coefficient. And if you check the units, then the units of the virial coefficient are mils, moles, per gram squared. So pi over c equals RT over m plus B RT times c. So if this varies with concentration, so this is concentration, that changes, then pi over c will change. What's this the equation of? Y equals a constant plus another constant times a variable. Y equals mx plus c.
Question of line, a straight
Straight
line.
line. This is the equation of a straight line. So if you plot pi over c against concentration, we'll get a straight line whose whose slope is BRT. These are all constants, and whose intercept on the plot is RT over M. The straight line. Pi over c is plotted against concentration, and the slope is BRT, and the intercept is RT over M. So if we make measurements of the osmotic pressure at a series of concentrations and extrapolate back to zero concentration, we get RT over M. If you know what the gas constant is, temperature, we can then work out, just rearrange the equation, we can get the molecular weight from RT divided by whatever the intercept is, after we've corrected our osmotic pressure to the appropriate units. And that's if we're working in the, that's if our osmotic pressure is in the CGS units. If we're in the SI units, then that will be kilogram per mole. And B, the slope, is divided by RT. So slope equals BRT, so B equals slope divided by RT. So we can work out what the virial coefficient is. If we wanted to, we could have used this form of the equation. The RT will go down here. So we plot pi divided by RTC equals 1 over m plus BC. So by plotting pi over RTC against concentration, we get an intercept of 1 over m, and the slope is B. That's an alternative plot to this one if you wanted to do that. So you could have plotted pi over RTC against C. If you'd done that, the intercept would have been 1 over m, and the slope would have just been B. It's your choice. And in fact, one of the assessed questions, folks, is on that. You are required to work out the molecular weight and the virial coefficient for a experimental solution of, I think it's some protein molecule. I think it's bovine serum albumin or whatever. So you should be able to do that question now if you manage to get the units correct and don't make any errors in the calculations. You should be able to get the molecular weight out and the virial coefficient. And when you do this, let me just check 1 second. I think, yes, make sure that when you do this calculation, make sure that your answer looks sensible. You should have a good idea of what to expect molecular weights of protein molecules to be. Many have molecular weights in the region of 10,000 to 100,000, and that certainly applies to the protein, which is part of the question on osmotic pressure. Okay, folks, and don't forget, contributions tend to zero as concentration approaches zero. And there are two contributions: co-exclusion phenomena caused by the volumes of the particles and the macromolecules getting in the way of each other, and then polyelectrolyte behavior, which comes from the charges on the macromolecules. Now, not all macromolecules possess charges. Many synthetic polymers are uncharged. Many polysaccharides are uncharged. And at the isoelectric point, for proteins, where the numbers of positive charges match the numbers of negative charges, positive charges from lysine, arginine residues, for example, negative charges from the acidic groups, aspartic acid, glutamic acid. If these charges balance each other at the isoelectric point, then the protein will also have a net zero charge. It doesn't mean it's uncharged, it just means the numbers of positive charges balance the numbers of negative charges. And proteins at the isoelectric point will also have no contribution from polyelectrolyte behavior. And the other thing is, if we increase the ionic strength of the solution by increasing the sodium chloride concentration or the magnesium sulfate concentration, when we did ionic strengths last week, by increasing the ionic strength of the solution, we can shield the charges on a macromolecule. And the greater the ionic strength, the greater the shielding of these charges. And that's why that's another reason why ionic strength is important, is that they can control the non-ideality behavior of solutions of macromolecules. By increasing the ionic strength, we can suppress charge interactions between macromolecules and hence reduce the non-ideality behavior. Okay, folks, and I think with that we'll have a short break before we deal with the next topic of heterogeneity. I mean, we could go into much greater detail as far as non-ideality is concerned. We can go into the equations describing co-exclusion and polyelectrolyte behavior, but that's more at a master's level. If you wanted to do that, you could always sign, not you, because you're doing a PhD, but for Hang Zhao and Zhang, if you want to go into this in the future in greater detail, we can recommend the MRes course in biomolecular technology, where we is one of the things we cover. Right, so we've dealt with not concentration, non-ideality. Let's deal with the heterogeneity of macromolecules now, and this means deviation from single molecular weight behavior. We've seen this already in our descriptions of proteins, and we also mentioned polysaccharides, that proteins are very precise structures. generally speaking, they have specific molecular weights because they're coded by a genetic template. And obviously you get species variations between the proteins that are produced for a certain type of protein, myoglobin, or maybe a plant protein of some sort. But the template ensures a consistency of the size and molecular weight of the protein molecule that's being manufactured. Now, that doesn't apply to other types of molecules like polysaccharides, for example. I mean, proteins, there's enzymes involved with proteins, but as I said, the association process, into assembly process is controlled. Whereas with the assembly of polysaccharides, again, synthesized using enzymes from monosaccharide precursors. Because there's no template to direct the synthesis, what happens is that you'll get a distribution of sizes. And when a polymer or macromolecular solution is monodispersed, then they all have the same molecular weight. So albumin will have a precise molecular weight. Again, it depends on the species, but it'll be around 45,000. And we say all the well-behaved, that means proteins which are synthesized by genetic templates, which they all are. There can be changes due to mutations in the genetic system and things, but generally speaking, during the time course of the production of a protein, the genetic template mechanisms are intact, so you get a consistent product. Nonetheless, you still can get variation in molecular weights of proteins if they are self-associating. That means that they are involved in some sort of assembly process to give oligomers, dimers, trimers, and whatever. So heterogeneity can arise from two types. One is polydispersity, where you have a natural distribution of molecular weight, and polysaccharides fit that example well. Also, synthetic polymers would also be polydispersed. But you can also get departure from homogeneity through self-association behavior of macromolecules forming dimers, trimers, tetramers, and things. But if all the molecules are in, say, the tetrameric state, as in hemoglobin, or in the dimeric state, such as beta-lactic globulin, then the system will still be homogeneous because everything is dimer, or everything is tetramer, or everything is monomer. It's when you get a mixture of monomers and dimers, dimers and tetramers, trimers and monomers, or whatever, then you get departure from homogeneity, we call heterogeneity. So two types of deviation from homogeneity. One is through polydispersity, through the natural difference in molecular weights caused by the different assembly processes, which are either controlled by template or not. If it's not, then you'll get polydispersity. So polydispersity contributes towards heterogeneity, but also we can get self-association and aggregation phenomena, and that also contributes to heterogeneity. And so when describing heterogeneous systems where we have different molecular weight materials present, we can describe the molecular weight by an average of some sort. Now, we can't just say average because the value you get for the average will be different depending on whether you average over the number concentrations of the species of different molecular weight or the weight concentrations of species of different molecular weight. The number average is the average over the numbers of molecules or molar concentrations with different molecular weights. And the weight average molecular weight is average over the weight concentrations with different molecular weights. And we give the number average molecular weight the symbol M subscript N, and the weight average molecular weight the symbol M subscript W. And these values will be different. Generally speaking, the weight average molecular weight will be greater than the number average molecular weight, except when you have a homogeneous or monodispersed system. When everything has the same molecular weight, then the weight averages and the number averages will be equal to each other. And different techniques give different types of molecular weight average. Techniques like osmotic pressure, which we've just been describing, are known as colligative techniques that depends on the numbers of molecules, and these give what's called the number average molecular weight. But there are other techniques based on light scattering and sedimentation techniques, which give directly the weight average molecular weight. And also you can manipulate data to give the number average as well. But the prime average molecular weight is the weight average from these techniques like light scattering and sedimentation equilibrium. So which technique you apply can give you different types of average molecular weight. And that's important to know. And the fact that these numbers are different is useful because it gives us a way of quantifying or describing how heterogeneous or how polydisperse a system of molecules are, from simply the way that the MW and MN values are different. It's actually the ratio of the two, which we call the polydispersity index, which gives a measure of the polydispersity. And there are different formulae for calculating these two molecular weights. So the number average molecular weight is the average over the number concentrations of molecular weights of different species. So it's a sum of Ni, Mi, where N is the number concentration or numbers of molecules. Mi is the molecular weight of a particular species of molecule, and divided by the sum of the total numbers of molecules. So that's the number average molecular weight. And instead of numbers of molecules, we can use the molar concentrations of molecules, because the molar concentration is simply the number concentration divided by Avogadro's number. So we can use numbers of molecules or numbers of concentrations or molar concentrations here. The weight average molecular weight is the average over the weight concentration of molecules of different species, averaged over all the species. So it's the weight concentration, C, times M of a particular species, and you sum all the different species up, divided by the total weight concentration. So that formula for number average molecular weight in terms of numbers, molecules, or molar concentrations, divided by the NIMI sigma divided by the total numbers of molecules, or weight concentration, so the weight average molecular weight, which is the sum of the weight concentration times the molecular weight of each species, summed over all the species, divided by the total concentration. Number average and weight average molecular weights. But because the molar concentration is related to the weight concentration by molecular weight, the molar concentration is the weight concentration divided by molecular weight. Then if you divide this by molecular weight, you just end up with the weight concentration. And similarly here, Ni becomes Ci divided by I. And similarly with the weight average molecular weight, this translates to sigma NiMi squared divided by sigma NiMi, or in terms of molar concentrations, small ci times mi squared divided by sigma small ci times mi. Right, that may seem a bit confusing. So the best way to understand this, what's the best way to understand this, folks? Anybody? Well, the best way is to do an example. So these formulae look complicated, but if we do an example, we can see how straightforward this is. And when you've worked out the weight average molecular weight and the number average molecular weight, you can work out this polydispersity index, which is the ratio of the weight average molecular weight to the number average molecular weight. And as I said before, for a monodispersed solution, the weight average molecular weight equals number average molecular weight. Polydispersity index will be 1. But generally speaking, polydispersity molecular weight average molecular weight will be greater than the number average molecular weight, and the polydispersity index will be greater than 1. Okay, let's do an example. Let's stop sharing screen. I go to that. Okay, can you see me now? Yeah. Okay, can you see the board? So pull the board a bit closer. It's still in range. Okay. Not too shiny.
Yeah, that's clear.
Yeah.
All right. So let's consider a solution. This is a special solution, just contains 3 molecules. All right. So there's our container. Okay. And in this solvent, we have can you see that 2 spherical-like molecules?
Yeah.
You see that?
Yeah.
Okay. So these represent ovalbumin. So we've got 2 molecules of albumin. And this is a special type of albumin, okay, whose molecular weight, molar mass is 50,000 grams per mole. Can you all see that? So 50,000 gram per mole for ovalbumin. Now we're going to have 1 molecule of this. Okay, and this is a dimer of myosin. So this molecule here is myosin, and its molecular weight or molar mass we're going to approximate as 500,000 gram per mole. So we've got 2, looks a bit like a silly face, isn't it? We've got 2 molecules of albumin, whose molecular weight molar mass is 50,000 gram per mole, and 1 molecule of myosin, whose molecular weight molar mass is 500,000 gram per mole. So what is the number average molecular weight and weight average molecular weight of that solution? Well, the number average, Mn, okay, is sum of Ni Mi squared divided by the total numbers of molecules. So, right, let's take the first molecule, which is ovalbumin. And how many molecules of ovalbumin do we have?
2.
2. So it's 2 times its molar mass. So that's incorrect. It's NiMi over Ni. Sorry about that. That's incorrect. NiMi over Ni. Yeah. So 2 times the molecular weight.
50,000.
And the next molecule is myosin. So it's one of those times molecular weight 500,000 divided by the total numbers of molecules in the solution, which is
3.
3. So that comes out to be
200,000.
yeah, correct. That's 200,000 gram per mole. So we just check that. If it's an average, it's got to be between these 2 numbers. Okay, so is 200,000 between 50,000 and 500,000? Yeah, it is. So it looks about right. So the number average molecular weight of that solution is 200,000 gram per mole. All right, that's easy enough. Now we're going to do the weight average molecular weight. So we get on with this. So the weight average molecular weight, MW, is sigma I Ni Mi squared divided by sigma I N I Mi. Okay, so we've got, let's just keep that over there. So we've got 2 molecules of albumin again times 50,000 squared plus 1 times 500,000 squared divided by 2 times 50,000 plus 1 times 500,000. Right, guys, so what does that come out to be? Well, the bottom bit's easy. That's just 600,000.
I've done it by calculator. It's 425000.
Okay, what was the number on the top?
That's something like 255 and lots of those.
Because it's 425,000 then.
Yeah.
Okay, so the Mn is 200,000 and the NW is 425,000 grams per mole. Just check that's right. Just make sure that's between 50,000 and 500,000. It is. So even for that solution of 3 molecules, there's a big difference between the weight average molecular weight and the number average molecular weight. And so we have a polydispersity index, Pi equals MW over Mn, and that comes out to be
2.125.
okay. That's not a monodispersed solution because we expect the value of 1. That's quite a heterogeneous solution. That's how we use these equations to work out the average molecular weights. So although the formula looks a bit complicated, by the time you've done an example, you can do it. So do all 3 of you understand that?
Yeah, I understand.
Yeah.
Athika? Is that straightforward to work out?
Yes.
Right. So the important thing is you can't just say average molecular weight when dealing with a heterogeneous or polydispersed system. You have to specify the type of average. The type of average depends on which technique that you are using. And we can use that to our advantage because if we use different techniques, one which gives Mn and one which gives Mw, we can get the polydispersity of our polymer. And the reason why that's important, well, I can't think of an environmental example, Hang Zhao and Zhejiang, why polydispersity might be important. But from a food point of view, which is closer to the thinkers, say if we were using, or pharmaceutical point of view, say we were using preparations of polysaccharides for a food product, or for the production of a polysaccharide vaccine, one for food, one for medicine. And the requirements in terms of the precision or monodispersity of your material is different depending on the application. So for a pharmaceutical application, we expect a more consistent product with a low polydispersity compared to the use for a food product. But it's still important, because if you've got a very polydispersed solution of, say, pectin, it'll give a poorer quality gel compared to one where the molecular weights are more tightly defined. Problem is, to get very defined molecular weights for materials like polysaccharides and synthetic polymers, you have to put them through expensive fractionation procedures in order to get that better definition. So it all depends on what you want to use the product for, whether it's for food or for a biopharmaceutical or for something else. And it's the polydispersity index which represents the polydispersity. Or you can just, there are techniques which will record the actual distribution of the molecular weights directly. So the use of the polydispersity index, the weight and number, isn't so important. But this is a useful number to have. So molecular weight is important, and the polydispersity is important when describing polymer systems. And next time, well, next week is the demonstrations, but then the following week, I think Gleb will be talking about polysaccharides. And when we do so, we'll introduce another important set of parameters for describing these macromolecules in solution, and that's well, these are parameters which represent the flexibility of macromolecules. Parameters like the what we call the persistence length, but we'll deal with that next time. So having done this, you should be able to answer the next question on the assessed questions, which concerns the heterogeneity of molecules. So we're ticking along quite nicely.